Hello out there and welcome. This is Reimer Vochler from AKG Acoustics speaking to you from the head office in Vienna. Welcome to the first module of my online wireless training and thank you for your time and for your interest. What we want to talk about today is the basics of wireless transmission, the nature of electromagnetic waves and the propagation of those waves. But before we start, we will ask ourselves the very fundamental question: why would we use wireless equipment instead of cables, even though we get headache by only thinking about this technology? Well, after this training you will hopefully realize that it was only missing knowledge that was making you nervous when using wireless equipment. So, let's hop right into it and find out when we would use this mysterious technology. We would use wireless whenever cables are impractical. They could be a problem for the freedom of movement. Cables could be undesirable, an optical disturbance if we think about a tidy studio stage setup. They could be even dangerous. If cable runs through public area, people might stumble across them. Or cables are just not accepted by the artist or production manager. So they pay for the production, they make the rules. Those are all occasions when we need to use wireless equipment. Let's have a look on a very simplified example of a radio channel. On the front end we have here our audio signal, could be a microphone or a line signal, and this audio signal we want to transmit to a far distant place where our receiver is located, and we are now modulating our audio signal into a radio signal in the transmitter. We are sending it from the transmitting antenna all across the air to the receiving antenna, where in the receiver the signal will be restored back to our original audio signal, and from there we can distribute the signal like we are used to from the good old days of cables. But before we go any further, we have to understand a few very fundamental rules in radio transmission. One of which would be: every wireless microphone system must operate on one specific frequency. The frequency has to be legal to use in your country, must not be occupied by any other user, and should be separated with enough distance to an adjacent channel, whether it's your own or a third-party channel. Transmitter and receiver of a system must work on the same frequency. Otherwise they are not able to communicate. Two transmitters cannot be used with one receiver at the same time. Two identical radio channels in the same environment are not able to coexist. They would interfere with each other. Two transmitters operating on a close frequency at the same time can cause interference problems. Close frequencies are disturbing each other as well. Wireless microphone systems share the frequency range with other wireless transmission systems, like there are TV stations, radio stations or mobile phones. But when I say sharing the same frequency range, what range are we actually talking about? We are talking about the electromagnetic spectrum. On the lower end of the spectrum we can see very wide cycles of our waves. As we move further up, the cycles are getting smaller, frequency is getting higher, and on the very top end of the spectrum the frequency of the waves is already that high so that we can't even use them anymore for our wireless transmission. Our range that we focus on lies around here, and you can see here we use the wireless microphones, TV, broadcast, also mobile phones. A little further up, microwaves are taking their places on the electromagnetic spectrum. Further up we meet the visible light, starting with the infrared, going up to the ultraviolet light, and from there we will meet the X-rays, gamma rays, and even cosmic rays on the very top end. So important to know is that radio waves as well as light waves are part of the electromagnetic wave spectrum. They only differ in their wavelengths. If we convert the previous illustration to the bar on top here, we will find the same zones and divisions like before. Our interest is the range of the entire electromagnetic spectrum that is usable for wireless devices, and it is determined as radio wave spectrum. In this range, most of the radio communication is taking place, such like CB radios, astronomical radios, devices for military services or Coast Guard communication. For the use of professional wireless microphones, we are using the UHF range, ranging from 470 MHz up to 2.5 GHz. The UHF range itself is again divided into small fractions called TV channels. To take a closer look on those, we take a look onto the next slide. Again, here we have our TV channels, and the TV channels used for professional wireless microphones range from TV channel 21, which is about 470 MHz in relation, to channel 69, which would refer to 860 MHz. Every manufacturer of wireless equipment has to specify in what range of TV channels his product will work in. And this gives us the direct information in what frequency range the product will work in. We already have learned that a transmitter and the receiver must be able to work on the same frequency, so it's obvious that a transmitter of band 4, for example, which is up here on our bar, a transmitter of band 4 is not able to communicate with a receiver in band 7. So a frequency band is actually a portion of the entire electromagnetic spectrum, separated from adjacent bands to coordinate and organize the frequency allocation for private or public uses, to not get in the way of each other and disturb the reliable transmission. What's also interesting to know is that the European TV channel has a bandwidth of 8 MHz, whereas a TV channel in the US or in Australia has only 6 MHz of bandwidth. So that might lead to misunderstandings when ordering wireless equipment or wireless microphones in diverse countries of the world. So let's have a closer look onto the nature of a wave. A physical wave, whether it's a sound wave or a electromagnetic wave, is determined by a number of figures, which are the wavelength, the amplitude, the frequency, and the speed. So the wavelength is abbreviated by a Greek letter called lambda, and it gives us the distance between one wave peak to the next, or one zero crossing point to the next. So every full cycle is one wavelength. The amplitude gives us the energy of the wave, and is the distance between the peak and the trough of the wave. The frequency is the number of waves occurring within a unit of time, usually per second. And the speed of an electromagnetic wave is that of the speed of light, which travels at 300,000 kilometers per second. The speed of a sound pressure wave is traveling at the speed of sound, so that's 300 kilometers per second. When we talk about a frequency of 5 kilohertz, that means we have 5,000 cycles in 1 second. And if we speak about 5 megahertz, we have already 5 million cycles per second. Here we have a 3D model of an electromagnetic wave. What is significant is that it consists out of two vectors in perpendicular orientation. The blue vector for the magnetic and the red one for the electric portion of the electromagnetic wave. Such a wave is created by the vibration of an electrical charge, and this vibration creates a wave which has both an electric and a magnetic component. On this simulation we can see how the wave propagates by building its magnetical and its electrical climax and its zero crossings always at the same time. The electromagnetic wave also propagates in a vacuum and is defined as a spatial propagation of a physical value which transports energy but no matter, meaning they move electromagnetic energy through space and affect regions far remote from the origin of this energy. If a radio signal is traveling from transmitter to a receiver, it carries the information content that was previously modulated onto such an electromagnetic wave, being now the carrier of that information. That process is taking place in a transmitter from where the wave travels through space until it gets picked up by a receiver where the original information is demodulated and restored. This can be achieved by a portable hand transmitter transmitting to a stationary receiver, or vice versa, from a stationary transmitter to a portable receiver. Usually, audio information like speech or music is transmitted by sound waves which consist of air pressure variations over a large range of amplitudes and frequencies. These varying pressure waves can directly be perceived by the human ear. On the other side, the radio information is generally transmitted using only one frequency. This single electromagnetic wave is varied in amplitude, in the amplitude modulation, or varied in frequency, in the frequency modulation. But in that state it can never be perceived by the human ear. In fact, the wave itself is not the information, but rather the carrier for the information. The information is actually contained in the amplitude or frequency variation. Soon as a radio wave contains information, it is called radio signal. This was a little bit of physical background for the understanding of wireless transmission, but now I want to give you a rest and continue in my next chapter of Wireless Basics Part 1. In my next chapter you will learn some more interesting facts about propagation of radio waves and about physical handicaps of transmitting and receiving radio signals. Stay well and stay in tune. Reimer Fochler from AKG Acoustics.